This video, we're going to be going over stress, strain, and deformations, and how to calculate them. So we will be looking at axial loading. We'll be looking at torsion. Be looking at bending, and finally we'll look at thermal effects. So let's go ahead and just jump right in and look at our axial loading. All right, so this would be where you have a bar of some sort of material and you're just pulling it in tension or pushing it in compression. So this bar will have a length. Again, it'll have that tension or compression load P. And this bar will have some radius, and then it will also have this property E, which is the modulus of elasticity, or Young's modulus. All right, and then once you know all those properties or attributes about the material you're looking at, you can go ahead and find the cross-sectional area, which if you have a circular rod is going to be pi r squared or pi d squared over 4. Then you can find the stress, which we represent using sigma, which is just P over A, so that load divided by the cross-sectional area. And then we can find our strain, which we use epsilon, and that's just going to be sigma divided by our Young's modulus. And then finally we can find our deformation, which we use lowercase delta for that. So if we're in tension, this bar is going to get longer, but if we're in compression, then it's going to get shorter. All right. So that deformation, whether it's elongating or shortening, is going to be our strain times our original length. All right, so if we just look at an example of one of these, let's say we've got a bar of steel that it's 10 inches in length. It's being pulled in tension with 10 kips of force. And it's got a diameter of 2 inches and a Young's modulus of 29,000 KSI. So start by finding the area. So it's just going to be pi times d squared over 4, which is 3.14 inches squared. Then we can find our stress, which is just P over A, so 10 kips over 3.14 inches squared. And we'll get 3.18 KSI. Then we can find our strain, which is just our stress, 3.18 KSI, divided by our Young's modulus, which was given in the problem as 29,000 KSI. And we'll get 1.10 times 10 to the negative 4. Then finally, we can find our deformation or our elongation, and that's just going to be our strain, 0.10 times 10 to the negative 4 times our original length of 10 inches, so we're going to get 1.10 times 10 to the negative 3 inches. All right, so not too bad. Go ahead and pause the video and you can try one of these on your own. Let's go ahead and try this guy right here. So again, you've got a circular bar. It's got a length of 1 foot and a tensile force of 500 kips. All right, the radius is 1 inch and Young's modulus is going to be 29,000 KSI, so we're using steel. All right, so go ahead, pause your video, and then you can check your answer with the PDF below. It'll be number 1. All right, now let's go ahead and talk about torsion. So torsion would be if you had some material and you're twisting it. So you're applying sort of a moment to both ends, which is causing rotation. Now that can be done to a bar like this, or it could be done to a bar that's fixed into a wall. Either way, so in each of these cases, you're going to have an L length, L for the total length. You're going to have some applied torsion force or a torque. You're going to have a radius, and then you're also going to have a shear modulus of elasticity, which we use the letter G to represent that. All right, so the first thing we need to find in these types of problems is the polar moment of inertia, and we use the letter J to represent that. And for a circular bar, you can use pi r to the 4th over 2. Then you can find the shear stress. We use the Greek letter tau to represent that, and you're going to get your torque times the radius divided by that polar moment of inertia. And then finally, we can find our angle of twist. And we use the Greek letter phi for that. And so we're going to take our torque times the total length divided by G times J. All right, so if we had, for example, some bar that is 100 inches long, and we apply a torque of 100 kip inches, and the properties of this bar, G is going to equal 11500 KSI, and our radius is going to be 1 inch. All right, so again, we'll start with finding our polar moment of inertia. So we're just going to have pi times r to the 4th all over 2. So at 1.57 inches to the 4th. Then we can go ahead and find our shear stress tau. So we're going to take our torque, 100 kip inches times our radius, 1 inch, all over j, which we calculated above is 1.57 inches to the fourth. Put that all in your calculator, you'll get 63.7 KSI. Then finally we can find our angle of twist, which is just our torque of 100 kip inches times the length, which was 100 inches, divided by G 11500 KSI times J, which we calculated above, 1.57 inches to the fourth. Put that all in our calculator and we will get 0.55 degrees. All right, so go ahead now and try this one on your own. You've got a bar, it's fixed into a wall. We're applying a 20 kip foot torque. The bar is 10 feet long. The radius is 2 inches. And our shear modulus is going to be 11.5 times 10 to the 6th PSI. So go ahead and work that out. Make sure you're watching your units on all of this stuff. So I'd make sure everything is either in kip inches, or pound inches, or kip feet, or pound feet, all right? So make sure you're being consistent with your units. And then you can go ahead and check your answer. It'll be number 2 on that PDF. Okay, now we can go ahead and talk about bending. So bending occurs in things like beams, where if you have a load applied to them, there will be bending throughout this beam, all right? So if we've got, some distributed load, this beam will have some length to it, and we'll also have to know the cross section of this beam. So it'll have some base and some height. So the first thing you want to do is do your shear and moment diagrams to find your maximum shear and your maximum moment. So it looks something like that and something like that, all right? Where max shear is going to be WL over 2, max moment is going to be WL squared over 8. All right. Now, if you have a different loading than this, again, just do your shear moment diagrams, figure out your max shear and your max moment, and you'll be all right. So the first thing we need to find for this, after we find our max shear and our max moment, is going to be our moment of inertia. For a rectangular section, that's just BH cubed over 12. Then you can go ahead and find your max stress, and the equation for that is going to be my over I. So M is going to be your max moment that we got from right here. I is going to be your moment of inertia that we calculated right here. And then finally this Y is going to be the distance, so that max distance from your neutral axis to the outermost fiber. Okay, so if you got a rectangular section, more likely than not, as long as it's a the same material throughout, it's just going to be h over 2. All right, and then we can go in and find our Q, which is like the first area moment of inertia. And what that's going to be is this A prime times Y prime. So if we're looking at our cross section, we're again going to have our neutral axis. All right, so you're going to take this area here. That's going to be your A prime. So the area from your neutral axis to the outermost fiber. All right, so this area is your A prime. And then your Y prime is going to be that distance between your neutral axis and the centroid of A prime. All right, and then you can find your shear stress, which is VQ over IB. Max shear, Q that we just calculated, moment of inertia, B, which is this dimension here. Okay, so let's go ahead and run through an example of one of these. Let's say we've got a beam that is 1,000 inches long, and there's a distributed load on it of 100 pounds per inch. And the cross section of our beam is rectangular with a base of 2 inches and a height of 4 inches. All right, so just as we showed over here, we're gonna get M max equals W L squared over 8, which ends up being 125, 1, 2, 3, 4, 5 pound inches, which is also equal to 125.00 kip inches. And then we can find our Vmax as W L over 2, which comes out as 50,000 pounds or 50 kips. We can find our moment of inertia, which is going to be B times H cubed over 12, which comes out as 10.67 inches to the 4th. So now we've got everything. We can find our bending stress, which again is going to be our max moment from above. So right there, 125.00 kip inches times our y, which is just going to be h divided by 2, so 2 inches, over I, which we just calculated is 10.67 inches to the 4th, and we'll get 2343.7 KSI. Now we can go ahead and find our Q, which again is going to be A prime, Y prime. So if we draw this out, we need this area here. So this is going to be 2, this is going to be 2. And then we need this distance here, which is going to be 1 inch. So 2 inches times 2 inches times 1 inch equals 4 inches cubed. And then we can find our shear stress, our max shear stress. So which is going to be V, which we get from right here. So 50 kips times Q, 4 inches cubed, over I, 10.67 inches to the fourth, times B, which is this distance here, so 2 inches. Plug all that in and you'll get 9.4 KSI. All right, so you can go ahead now and try one of these on your own. Let's say we again have a simply supported beam with a length of 20 feet, has a uniform distributed load of 10 kips per foot, and a cross section with a base of 3 inches and a height of 5 inches. All right, so go ahead and find the bending stress and the shear stress for that beam. Again, watch your units, but you can check your answer with the PDF. It's number 3. Now finally, we're going to go over thermal effects. So when materials are heated or cooled, they expand or shrink. And so this will give us the strain caused by temperature differential is going to be alpha times T minus T naught, where alpha is just a coefficient of thermal expansion. It's just based on what kind of material you have. T is your final temperature, T naught is your initial temperature. And then you can find your stress by knowing the Young's modulus times the strain, and then your deformation is going to be the strain times the original length of your bar. So for example, if we had a steel bar that had an initial temperature of 20 degrees Fahrenheit, and we heated it up to 90 degrees Fahrenheit, and let's say alpha equals 13.1 times 10 to the negative 6 per degree Fahrenheit. E is going to be 29,000 KSI. And finally, the length of our bar is 36 inches. Sigma is going to equal 13.1 times 10 to the negative 6 per degree F times 90 minus 20 degree F. So these will cancel, and we will end up with 9.14 times 10 to the negative 4 for our strain. For our stress, we'll take that 9.14 times 10 to the negative 4 and multiply it by our E, which is 29,000 KSI, and we will get 26.6 KSI for our stress. And finally, for our deformation, we're again going to take that 9.14 times 10 to the negative 4, times it by the original length, which is 36 inches, and we'll get a deformation of 0.33 inches. So when you heat up the bar 70 degrees, it actually expands by 0.3 inches, which is kind of cool. So go ahead and try one of these on your own. So we're looking at a bar that is 20 inches long. It's got an alpha of 13.1 times 10 to the negative 6 per degree F. And it also has an E of 10,000 KSI. And the starting temperature is 70 degrees Fahrenheit, and the final temperature is 90 degrees Fahrenheit. So find stress, strain, and deformation of that bar. So again, work that out. You can check it with the PDF. It'll be number 4. And that concludes our learning for stress, strain, and deformation. So you can go ahead and run through the quiz until you've gotten all those right.